Namaste. Welcome to the talk on the second part of the mineral deposits related to chemical sedimentation. In today's lecture, sedimentary manganese deposits and seafloor ferromanganese nodules will be dealt. Sedimentary manganese deposits and their metamorphic equivalents produce the bulk of the world's output of manganese. Residual deposits are the other main source. In 1989, manganese deposits of Nikopol Basin in Ukraine and the Chaitura Basin in Georgia contributed about 9.1 million tons of ore, which amounts to about 41% of the world production in that year. The other important producers in 1989 are the Republic of South Africa amounting to 3.62 metric ton, Gabon 2.45 metric ton, Australia 2 metric ton, Brazil 1.8 metric ton, followed by India 1.1 metric ton. About 95% of the total world production of manganese ore is consumed by the steel industry. The remaining is used for multitude of purposes. Weiss in the year 1977 wrote that manganese is used in feed, food, fertilizer, fungicides, face bricks, frits, flax, fragrances, flavors, foundries, ferrites, fluorescent tubes, fine chemicals, ferric leaching and ferroalloys. Manganese is an oxidant, deoxidant, colorant, bleach, insecticide, bactericide, algicide, lubricant, nutrient, catalyst, dryer, scavenger and much more. The geochemistry of iron and manganese is very similar and the two elements might be expected to move and be precipitated together. This is indeed the case in some Precambrian deposits. For example, in the Koyana mining district in the Lake Superior region, manganese is abundant in some of the iron formations and forms over 20% of the ores. In other areas, there seems to have been a complete separation of manganese and iron during weathering, transport and deposition, so that many sedimentary iron ores are virtually free from manganese and many sedimentary manganese ores contain no more than a trace of iron. In the stratigraphic succession of several sedimentary manganese deposits, banded iron formations are encountered, but they are clearly separated from those of manganese. The best examples are from glacial-marine sequence of Santa Cruz Formation, Brazil and Coas Formation, Namibia, Itabira Group, Brazil and Kalahari Manganese Field in South Africa. Several workers have proposed that anoxia plays a significant role in the formation of sedimentary manganese deposits of shallow marine environments in intracratonic basins. Anoxia leads to an increase in the dissolved manganese in the deeper seawater of adjacent stable basins, and following a marine transgression onto a nearby platform, the dissolved manganese can be precipitated in the shallow oxidic zone of shelf region. Shallow marine manganese deposits are thus considered to be lateral facies of black shales formed in anoxic basins. Another enigma of manganese deposits is the almost universal restriction of land-based deposits to shallow water environments of deposition, whilst in modern deep sea areas and ocean floors, there is an unprecedented concentration of manganese in the form of manganese nodules. Roy in the year 1988 and Glasby in the year 1988 have estimated that whereas the total terrestrial manganese deposits amount to about 6.4 billion tons, deep sea manganese nodules formed since the lower Miocene, that is 12 million years ago, hold about 10 to the power of 11 tons of manganese, that is 16 times the manganese ore resources of the terrestrial deposits. Almost equally puzzling is the time distribution of economic manganese deposits, the first of which appear in rocks about 3000 million years old, that is towards the end of the Archaean, but these deposits are economically insignificant, particularly when compared with BIF deposits of this age. Large sedimentary deposits of manganese do not appear until the Paleoproterozoic, within which the world's largest known resource of manganese occurs in the Transvaal supergroup of the Kalahari field. Glasby in the year 1988 has estimated this as containing 5026 million tons of manganese compared with the world's total resource of 6376.1 million tons. Now, let us take a look at the world occurrences of manganese deposits. Prominent manganese deposits of Phanerozoic age include early Oligocene Nikopol and Chaitura, Cretaceous Imani Transdremt Belt in Morocco, Cretaceous Ulukent Gökçeberk in Turkey, Cretaceous Groot Island, Australia, Late Jurassic Molango in Mexico, Early Jurassic in Hungary, Late Devonian Karazhol in central Kazakhstan, Middle Ordovician Trojong in China, Neoproterozoic Santa Cruz Formation, Jacadigo Group in Brazil, Neoproterozoic Datango Sequence, Litano-Nantuo Ice Age in China, Neoproterozoic Chuos Formation, Damara Sequence, Namibia, Neoproterozoic Penganga Group in India, Paleoproterozoic Saucer and Gangapur groups in India, Paleoproterozoic Franceville Group in Gabon, Paleoproterozoic Birimian Group in West Africa, spread over Ghana, Ivory Coast, Burkina Faso, Mali, Eastern Liberia and Guinea. Paleoproterozoic Itabar Group, Minas Supergroup in Brazil, Paleoproterozoic Kalahari Manganese Field in South Africa and Paleoproterozoic Runike Formation Transvala Supergroup in South Africa. Late Archean manganese deposits are of limited occurrence and found only in India and Brazil. Absence of sedimentary manganese deposits in the early part of the Archean eon is attributed to the fact that the early part of the Archean with an extremely oxygen deficient atmosphere and hydrosphere system was geochemically hostile to manganese precipitation, though plausibly ferrous and manganese was substantially released by high temperature endogenic hydrothermal solution and stored in contemporary deep oceans. Late Archean sedimentary manganese deposits in Chitradurga Group, Dharwar Craton and Iron Ore Group, Singabam Craton of India provided geological evidence for the exact timing of the availability of the photosynthetic oxygen in atmosphere and hydrosphere system. 3.1 GA old sedimentary manganese deposits in the Singabam Craton are associated with BAF and the latter is found to contain algal stromatolites and microfossils. In the Dharwar Craton, which is more than 2.6 billion year old, sedimentary manganese ore beds are underlined by stromatolitic limestone. The presence of cyanobacteria in stromatolitic limestone indicates supply of photosynthetic oxygen, which evidently induced precipitation of manganese oxide and hydroxide. Therefore, the localized photosynthetic oxygen production in basin margin euphotic zone played a vital role in generating shallow water manganese oxide deposits of the Dharwar Craton of 2.7 to 2.6 billion year age. According to Roy, the initiation of drastic change in the late Archean Earth's exogenic environment has taken place at about 2.7 billion year ago. The severely oxygen poor early Archean atmosphere was initially paired with totally anoxic oceans. The introduction of oxygenic photosynthesis in basin margin euphotic zones produced restricted oxygenated domains. Towards the Archean Paleoproterozoic boundary, such oxygenation was triggered by the introduction of photosystem 2. This restricted and perhaps transient establishment of the ratio of manganese divalent to manganese tetravalent chemocline led to modest late Archean initiation of sedimentary manganese mineralization. After modest initiation of manganese ore sedimentation during late Archean, the Paleoproterozoic was replete with gained and large size sedimentary manganese deposits formed in a variety of geological settings. The Mesoproterozoic was practically barren, while during the following Neoproterozoic time, most manganese deposits are restricted to glaciogenic sequences. The Phanerozoic eon shows considerable diversity in ages of the deposits. Manganese concentrations were relatively small in the Paleozoic and substantially large in the Mesozoic era. During the Cenozoic, while grain-size concentrations of land-based deposits were formed during the early Oligocene, the milieu of sedimentary manganese mineralization in the form of manganese nodules was shifted to the oceanic realm during the rest of the era. Now, let us consider late Archean manganese deposits. In Brazil, granulates in the Jequié complex in Bahia state host a manganese silicate carbonate proto that yielded small supergene manganese oxides. More important deposits occur in the San Francisco Craton in the greenstone sequence of the Rio das Velhas supergroup Minas Gerais. The base novel plume group of about 2.78 billion year old comprises volcanic rocks overlain by shallow water metasedimentary rocks, including black shales hosting manganese silicate carbonate proteors. This proteor was formed by metamorphism of manganese carbonate admixed with silica and other impurities with ubiquitous free carbon, which was deposited in reducing environment. The black shale could possibly be linked to mantle plume activity. The manganese silicate carbonate proto on later supergene alteration produced commercial grade manganese oxide deposits. In India, late Archean manganese deposits occur in several geological sequences. In the iron ore group, Singabam Craton, eastern India, dated as about 3.1 billion year old, manganese oxide ore beds occur in the topmost upper shale horizon, immediately overlying a thick sequence of BIF. Algal stromatolites and microfossils were described both from the BIF and the upper shale horizon that host the sedimentary manganese ore bodies. The shallow water depositional features in the sequence and the occurrence of stromatolites strongly indicate a shelf environment of the iron ore group rocks, including the manganese deposits, where local photosynthetic oxygen production was inferred. In the eastern Ghats granulite belt on the east coast of India, important manganese deposits are interbedded with pilitic rocks, calc-silicates and garnetiferous feldspathic quartzite of the chondrolite group. The sedimentary protolith package was deposited in shallow water stable shelf milieu. The metamorphosed manganese oxide ores and the manganese silicate carbonate rocks present in the sequence are spatially and temporally separated. In the Dharwar supergroup of the Dharwar Craton, southern India, the Anga Chatradurga group hosts sedimentary manganese oxide deposit restricted to basal Vanivelas formation. These occur as banded manganese oxide chert formation in a stable shelf setting. Intertidal to subtidal stromatolites occur profusely in close association with cherty dolomite banded manganese oxide chert assemblage, indicating deposition within the basin margin euphotic zone where photosynthetic oxygen was evidently generated. The volcanosedimentary sequence of the Sandur group in the eastern block of the Dharwar Craton was deposited in shallow marine condition coeval with the lower part of the Chatradurga group. The stromatolitic limestone of the Deogiri formation, which is associated with the manganese oxide deposits, indicates supply of photosynthetic oxygen, which evidently induced precipitation of manganese oxide and hydroxide. Now coming to Paleoproterozoic manganese deposits, the Paleoproterozoic earth system witnessed a discernible rise of atmospheric oxygen levels around the Archaean Proterozoic transition, and this event initiated formation of large manganese deposits in the very early Paleoproterozoic era. Sedimentary deposition of iron and manganese is intimately related to stratified oxic and anoxic ocean system and marine transgression and regression episodes. During transgression, manganese oxyhydroxide gets deposited on continental shelves above oxic-anoxic interface. Above the redox cline, but in the absence of a substrate, manganese oxyhydroxide formed transiently would have been drawn below into the anoxic zone and dissolved on reduction. In certain cases, during progressive transgression, manganese oxyhydroxides earlier precipitated on the continental shelf could also sink back to the anoxic zone, enriching it in dissolved manganese. Thus, a manganese pump could have been operative from an oxic to the anoxic zone. Such enhanced concentration of manganese on reaction with originally derived bicarbonates through degradation of settling planktons from high primary productive zones during transgression produced manganese and calcium carbonate in pore water of the bottom sediments. This process can be applied to explain the formation of manganese carbonate in the organic rich part of the oceans. Impressive event of sedimentary manganese ore deposition was evident in the very early Paleoproterozoic in the Transvaal supergroup of the Kaapvaal Craton, South Africa. Two 1 meter thick manganese oxide ore beds are interstratified with Runeke iron formation of the Kigoa subgroup. This marks the modest initiation of Paleoproterozoic shallow shelf sedimentary manganese mineralization in Griqualand West area during transgression of manganese rich anoxic deep water of a stratified ocean. It was followed by a spectacular event of manganese deposition of the Kalahari manganese field in the 2.5 billion year old Hotzell formation of Postmusburg group. This is the largest manganese accumulation amounting to about 13.6 billion tons on land located in a single geological sequence. The Hotzell formation consists of interbedded BIF and manganese ore corresponding to repeated transgression and regression cycles. The Kalahari manganese deposit is composed primarily of brunite, kunthanorite, hematite assemblage which shows late diagenetic or metamorphic change to osmanite, braunite, bixbyite, manganese calcite. This assemblage was further partially affected at a much later stage by epigenetic fault controlled hydrothermal metasomatism leading to upgradation of the ore. Significant deposits of manganese oxide ore occur as beds and lenses intercalated with BAF and dolomite in the Itabira group of the Paleoproterozoic platformal Minas supergroup in Minas Gerais, Brazil. The BIF dolomite manganese oxide ore association is time equivalent with those of the earlier described Hotzell formation, Transvaal supergroup, South Africa. Manganese oxide ore of the Minas Gerais was derived by pronounced supergene alteration of metamorphosed manganese silicates and carbonate rock enclosed in a graphitic phyllite. Klein and Ladera suggested that BIF and manganese oxides were formed by enrichment of hydrothermally derived metals in the deep anoxic part of the ocean and their transfer by transgression upwelling to stable oxic shells. The Paleoproterozoic greenstone belt of the Birimian supergroup in the West African Craton spread over Ghana, Ivory Coast, Burkina Faso, Mali, Eastern Liberia and Guyana hosts important manganese deposits. The deposits at Ceuta in Ghana, Tambo in Burkina Faso, Ziomogolo in Ivory Coast are particularly important in this 1400 kilometer long belt. In the lower Birimian greenstone sequence, fairly evenly placed belts of isoclinically folded volcanic rocks, mainly mid-oceanic ridge basalt type basalts with subordinate andesite, dacite and minor rhyolite show nearly parallel deposition, spatial continuity and overlapping of ages with a package of chemical sediments. Chert and calcium iron manganese carbonate of this package are closely associated with black shales adjacent to the volcanics. The manganese carbonate protor occurs as thick beds and lenses and are interstratified with black shale, chert and volcaniclastic rocks that are penicontemporaneous with basalts in an extensional tectonic regime, plausibly an intracontinental rift setting. The manganese carbonate rocks were formed in shallow marine conditions immediately below the shelf break. The carbon isotope values of the manganese carbonates delta C13 values ranging from minus 5.0 per mil to minus 15 per mil. In the protozoes indicate variable contributions of organic carbon in an anaerobic conditions. This indicates that manganese was concentrated in anoxic deep sea water and that rhodochrosite was formed most likely by organic carbon mediation during early diagenesis from a manganese oxyhydroxide progenitor. Hydrothermal supply of manganese for the formation of manganese protozoa including albandite in a strongly reducing alkaline condition was envisaged by Mickey et al. In the year 1999. The sedimentary rocks of the Birmingham sequence were metamorphosed to low to medium grade. Later, supergene enrichment of the manganese protozoa produced manganese oxide deposits. The trans-Amazonian orogenic belt of the Guiana Shield spread over Guyana, Suriname, French Guiana, Venezuelan Guyana and the Brazilian territory of Amapá is characterized by a greenstone belt containing several manganese deposits. Manganese silicate oxide and silicate carbonate protozoas are interstratified with metamorphosed carbonaceous black shales, pilitic rocks and quartzites. These metamorphosed manganese protozoas were oxidized and enriched by supergene processes during later weathering. The trans-Amazonian orogenic belt of the Guiana Shield extends into the Brazilian territory of Serra do Navio. The Amapá series Brazil consists of the lower Jornal group and the upper Serra do Navio group. The latter comprises 3 rhythmic cycles of sediments, each consisting of a basal quartzite overlain successively by peelites and graphitic black shales metamorphosed to amphibolite facies. The manganese carbonates and silicate protozoas all are enclosed in graphitic black shales. The more extensive protozoa consists of rhodochrosite, minus spessartine, rhodonite, tephrite, graphite and occasionally albandite, pyrite and other sulfides. This assemblage strongly resembles that of the manganese carbonate protozoas of the Birmian supergroup West Africa of similar age. The formation of diagenetic manganese carbonate and albandite within carbonaceous black shales suggests that anoxic matter burial event. The rhythmic cyclicity of the sedimentary pile of the Serra do Navio group could possibly be related to marine transgression regression cycles. The manganese carbonate and silicate protozoas were later enriched by oxidation during weathering, producing manganese oxide ore deposits. In Gabon, the Paleoproterozoic Francevillien series hosts the Monda deposit, which is the largest manganese carbonate concentration developed in organic rich black shales. These deposits are interbedded with pyritiferous black shales, dolomite and sandstone at Okoma, Bafola and Bangombe plateaus. In these plateaus, the manganese rich horizon is underlined by BAF of sulfide, carbonate and silicate facies from bottom upward. In the FBI unit, the thick carbonaceous black shales were formed in anoxic deep water in a stratified ocean system. The formation of these black shales may be correlated to the globally large scale burial event of organic carbon of similar age. Based on the delta C13 values of the black shale and rhodochrosite of the diagenetic manganese carbonate ore, it was inferred that dissolved manganese was supplied to the oxic zone from a reducing seawater source during the transgression regression cycle in an epicontinental basin. Manganese oxyhydroxides thus formed was dissolved again on burial to the anoxic zone and reacting with bicarbonate produced manganese carbonates. High grade manganese oxides were produced by supergene oxidation of the manganese carbonates. The Paleoproterozoic saucer group in Madhya Pradesh and Maharashtra India hosts large sedimentary manganese oxide deposits in different stratigraphic levels of the shallow water shelf sequence of orthoquartzite carbonate shale, which is free of volcanic rocks. The whole sequence, including the manganese rich components, were subsequently deformed and metamorphosed to different grades up to upper amphibolite facies around 1525 plus or minus 25 million years back. Important manganese oxide deposits with braunite, bixbyite, hollandite, jacobsite, haussmannite, riedenbergite occur interbanded with manganese silicate oxide rocks enclosed in orthoquartzite metaphylites of the Mansar formation and less commonly as conformable lenses in carbonate rocks of the older Lohangi formation. The manganese silicate carbonate rocks occur as pockets in the manganese oxide hoar horizon in the Mansara and the underlying Lohangi formations. The principal progenitor of these rocks was manganese carbonate, which was shown to have been diagenetically derived from manganese oxides by reaction with calcareous spottings in isolated evaporating pools. The manganese oxide rich sediments were deposited on shallow shelves above the Mn divalent to Mn tetravalent redox interface during a sea level high stand irrespective of the nature of substrate. Example, carbonate substrate of the Lohang formation. The Gangapur group in Orissa, India, considered coeval with the above described saucer group, hosts metamorphosed manganese oxide ores and manganese silicate oxide rocks interbanded with pilitic schists of the Goirajur formation. The manganese rich protolith was possibly deposited through upwelling of manganese rich anaxic deep ocean water. The prominent black shale facies in the Kumarmunda formation overlying the ore bearing sequence may represent the concluding stage of the global event of organic carbon burial and supports the model of a genetic link between shallow marine manganese deposits and the black shale basins suggested by Force and Cannon in the year 1988. Now, we shall take a look at the Neoproterozoic manganese deposits. The Neoproterozoic era records the assembly and breakup of supercontinents, repeated glacial cycles and the resultant formation of ore deposits, particularly those of iron and manganese. Several ice ages with interludes of warm periods were identified in the later half of the Neoproterozoic era. Among these, the most studied and globally extensive are the Strutian and the Varangian glacial events. The Strutian event has been documented from the Ractian group, northwest Canada, and the Choos formation, Damara sequence, Namibia. Glaciogenic formation related to the Varangian event are recorded in the Chang'an and Liuantou Nanchu iso ages in South China and in the Jacadigo group. These glaciogenic sequences host manganese deposits and or BIF. Many of the Neoproterozoic glaciogenic horizons record presence of BIF or iron rich sediments, whereas only a few sedimentary manganese formations occur with or without BIF associated with glaciogenic horizons. In the Damara sequence Namibia, the glaciogenic Coas formation at Odjosondo hosts both BIF and manganese oxide beds in a transgressive regressive sequence. The transgression was related to the breakup of the Rhodania supercontinent involving the Kalahari and the Congo cratons, leading to thermal subsidence and flooding of the continental margins. A deep water condition was thus created on the shelf on which the ore beds with the metals derived from hydrothermal sources were deposited with minimal detrital input. Thus, the manganese oxide beds, which are conformably enclosed within BIF, constitutes interglacial transgressive regressive sequence. The Varangian Liuantou Nanchu glacial interglacial horizons in the South China hosts important deposits of manganese carbonate interbedded with black shales of the interglacial Datangopo sequence. The manganese carbonates were probably diagenetically derived from manganese oxyhydroxide precursors through organic carbon mediated reaction. BIF is absent in the sequence. At Urucum, Brazil, the Santa Cruz formation of Jacadigo group consists of 4 manganese oxide beds intercalated with BIF. The lowest and the uppermost units are associated with clastic sediments and glaciomarine dropstones. The manganese oxide and BIF were formed in interglacial stages during marine transgression. The metals presumed to have been derived either from rift-related hydrothermal source or from continental weathering, or both were pre-concentrated in dissolved state in stagnant, high saline, oxygen deficient seawater beneath the ice cover during glaciation. During glaciostatic sea level rise, dissolved manganese and or iron stored earlier in seawater under ice cover were transferred to the drowned continental shelves, which subsided during rifting. With decrease in salinity and on upward advection, the dissolved metals were precipitated in relatively shallow, wherein manganese proximal and deep water, here Fe distal on shelves. The Neoproterozoic sedimentary sequence of the Penganga group in Godavari Rift Basin, Andhra Pradesh, India consists of finely laminated thick horizon of limestone developed in a transgressive phase horse manganese oxide ore beds interlaminated with chert. In the ores, primary todrokite and birnasite were partially or wholly converted diagenetically to manganite, brownite and bixbyite following a deoxidation path. A localized occurrence of manganese carbonate is also noticed in this sequence. A terrigenous source for manganese was favored by most workers except who inferred a hydrothermal derivation. In Morocco, Neoproterozoic volcano-sedimentary sequence with suspected tillites in the anti-Atlas region hosts stratiform manganese oxide deposits at Tiono, Migodan and Aufront. The deposits indicate the possibility of their derivation related to glacial interglacial events accompanied by rift-related hydrothermal activity. Now, let us understand some of the important Paleozoic manganese deposits of the world. The earliest sedimentary concentration of manganese during the Paleozoic occurs at Tian-Tai-Shan in Shaanxi province, Russia. At Tian-Tai-Shan deposit, manganese carbonates are hosted in black shale carbonate sequence of the early Cambrian Tanapo formation. Carbon isotope values of the rhodochrosite and kunthanohorite, wherein delta C13 values ranges between -7 to -7.7 per mil, suggest their derivation from seawater bicarbonate and bacterially mediated diagenesis of manganese oxide precursors. Dissolved manganese was stored in anoxic highly saline ocean below the ice cover during Neoproterozoic glaciation. Subsequent rifting with outgassing and warming led to deglaciation and sea level rise, assisting transfer of dissolved manganese to the shallow inundated shelf areas. Precipitation of manganese oxyhydroxide followed, which were diagenetically converted to manganese carbonates. The early Cambrian manganese carbonate deposit at Usins, Siberia, interbedded with manganese bearing limestone and black shale, has been assigned a terrigenous sedimentary origin. The organic carbon bearing limestone and black shale association suggests only diagenetic formation of manganese carbonates by organic carbon mediation. The Middle Ordovician Tozhuang deposit in Hunan province, South China, consisting of manganese carbonate interbedded with black shale, iron manganese bearing limestone and calcareous clay stone in a shelf setting marks the transition of peak marine transgression with initiation of regression. During transgression, manganese oxyhydroxides are inferred to have precipitated initially on transfer of dissolved manganese from anoxic deep sea to the oxic shallow shelf, followed by their diagenetic change to manganese carbonates. The most significant manganese deposit of the Paleozoic era occurs in central Kazakhstan in Vidya-mitra trough in the Upenskik tectonic zone. Major deposits of manganese oxide and carbonate of late Devonian age occur in the Atasu region, represented by the important one at Karadziol. Here, bedded and lensoid manganese and iron ores, occasionally with polymetallic sulfides, occurs in different stratigraphic horizons. The most extensive manganese deposits with a mineralogy of braunite, haussmannite, rhodochrosite, jacobsite with minor hematite and magnetite occur in shallow water upper Karadziol sedimentary sequence. The ore-bearing horizons are underlined by mafic to felsic volcanics and topes. Manganese and iron deposits were formed as sediments lie down in different intervals during widespread glacio-eustatic rise in sea level. The early Carboniferous deposit at Umbogma, southwest Sinai, consists of zoned manganese and iron oxide ore bodies forming lenses in dolomite. The manganese ores are sedimentary, diagenetic in origin, formed as evaporates in tidal pools during marine regression. A shallow marine sedimentary origin was confirmed by Magaritz and Brenner in the year 1979. Now coming to Mesozoic manganese deposits, during the Mesozoic era, widespread accumulation of significant manganese deposits is recorded. All these are genetically related to global sea level changes caused by tectonic forcing and volcanism. Small but illustrative sedimentary manganese carbonate deposits of early Jurassic age occur in association with black shales in rifted basins in continental margins in Austria, Germany, Hungary, Italy and Switzerland. These European deposits are coeval and were formed in anoxic conditions just prior to black shale deposition. The best studied deposits at Urkut, Hungary consists of rhodochrosite beds in stratigraphic intervals of Radiolarian Marl horizon just below black shales in a marine sequence. Euxinic conditions prevail during sedimentation of the marl stones. Polgari et al. In the year 1991 inferred that dissolved manganese, possibly of hydrothermal source, initially accumulated in anoxic seawater. It was then transferred to the oxic domain close to the basin margin to precipitate as manganese oxyhydroxide, which on consequent burial into the anoxic zone was dissolved again and on reaction with originally derived bicarbonate was converted to rhodochrosite. At Molango, Hidalgo State, Mexico, a gained rhodochrosite deposit is restricted to the Chipaco facies in contact with the underlying Santiago formation composed of calcareous and pyrite-rich black shale. The manganese deposits were possibly formed either at the onset of transgression or at the culmination of regression. Pyrite-bearing manganese carbonate occurs in the basal part of the Chipaco facies. This basal part is deduced to have deposited in anaerobic condition, while the older Santiago formation was laid down in a euxinic environment. The manganese carbonate ore is interpreted as organic matter mediated diagenetic product of a manganese oxyhydroxide progenitor. Okita favored fluvial transport of manganese derived from continental source to the depositional basin. At Groote Eylandt, Australia, a large stratiform manganese oxide deposit is hosted in Mulaman beds which overlies unconformably Middle Proterozoic sandstone in the intercratonic Carpentaria basin. The hoar horizon, almost entirely composed of manganese oxide, pissolites and oolites, directly overlies a pyritiferous and glauconite bearing calcareous siltstone containing rhodochrosite and manganese calcite. The manganese oxide pissolite and oolites show both normal and inverse graded units formed by primary concretionary process in a shallow marine environment. It was also inferred that manganese supplied by continental runoff was concentrated in dissolved state in a deep oxygen deficient part of stratified ocean during sea level rise in late Albian before final transfer to shallow oxic shelf for deposition. In Morocco, important deposits of sedimentary manganese oxides are hosted in 3 levels of a diagenetically modified dolomite horizon of Cenomanian Turonian age in the Imni Transdremt belt. Fossil evidence from a carbonate unit in the Imni area indicates a marine, probably an inner shelf depositional environment. A rapid marine transgression event was responsible for the supply of dissolved manganese from the anoxic deeper part of a stratified ocean to the shallow oxic shelf. It was inferred that manganese was contributed to the anoxic deep water from the continental weathering zones. In Turkey, the Oligocene and Geochemistry deposits with manganese silicate oxide carbonate ores occur in Cherty limestone in a black shale sequence. The manganese silicate oxide carbonate rocks possibly represent progenitors of oxide and carbonate facies merging into one another. Carbon isotope values for the manganese carbonatite, that is kunthanarite and rhodochrosite, suggest their organic carbon mediated diagenetic derivation. Both deposits were formed during marine transgression regression events. Now, the Cenozoic manganese deposits. Gained deposits of sedimentary manganese oxide ores of early Oligocene age occur at Chaitura, Bolshoi, Tolmark and Nikopol, and in the northern Ural, Sayan and Baikal regions of Russia. All these deposits were formed in intracratonic settings. The deposits share most of the following features. Number 1, several ore beds and lenses interstratified with or enclosed in orthoquartzites or glauconitic claystone. Number 2, oolitic and pissolitic structure of the ores, and number 3, a basinward facies change from oxides to carbonate. A diagenetic change of manganese oxide to manganese carbonate was advocated. The stratified ocean model for the origin of these deposits was first conceived by Soponikov in the year 1970. He proposed that in the Paleogene Mycop basin, anoxic deep water enriched in dissolved manganese on upwelling to the shelf region led to the oxidation and precipitation as manganese oxide and hydroxide. A transgressive regressive cycle in a restricted arm of the Parathetis was considered responsible for the formation of Chaitura deposit, where manganese oxide and carbonate oolites and pissolates showing both normal and reverse graded bedding were formed by accretion in a shallow marine setting. It was proposed that terrestrial weathering supplied manganese, which after concentration in the deeper anoxic zone of the stratified ocean was advected during transgression to the oxic zone and precipitated as manganese oxyhydroxide on the shelf. Carbon isotope data from the manganese carbonates of Nikopol, wherein delta C13 values ranges between -9 per mil and -16 per mil with a mean of -11.9 per mil, suggest an early diagenetic derivation of manganese carbonate from initially precipitated manganese oxyhydroxides. It is now accepted that the major land-based sedimentary manganese deposits of Phanerozoic age are genetically related to stratified ocean system, marine transgression and climate warming. All these phenomena can ultimately be related to tectonic intervention. Based on microfossil evidence, the early Oligocene time was inferred to have been warm, which agrees well with the transgression related Nicopol, Chaitura and similar deposits of this age. Table 1 compiled by Roy in the year 2006 provides age-wise distribution of selected manganese deposits. During the period postdating the early Oligocene, particularly since the late Miocene time, the locale of sedimentary manganese deposition was distinctly shifted from the continental shelves to the deep sea floor since 15 million years, producing iron manganese nodules and crusts. This was particularly aided by changes in ocean circulation patterns and the onset of the oxygenated polar bottom waters. The dissolved manganese concentration and its deposition in such cases correspond to glaciation and deglaciation respectively. The last topic of today's lecture is on manganese nodules. The deep oceans are sediment starved. Since oceanic crust is produced at mid-oceanic rises and consumed in subduction zones, the average age of oceanic crust and thus of the sea floor is only a few tens of millions of years. With only a few millimeters of sedimentation per year, the sediment load on deep oceanic crust is typically thin, consisting of a few centimeters of siliceous oozes, ochres, diatoms and radiolarian and other debris. The ooze appears to become more anomalously transition metal rich as a mid-oceanic rise approached, but one of the startling discoveries of the marine world was that of a pavement of black nodular golf ball sized accretions of manganese and iron oxide composition carpets much of the ocean floor. Volumes of literature have cropped up on every conceivable aspect of these exotic materials since their discovery and bulk collection by the HMS Challenger during the period from 1872 to 1876. These ferromanganese or manganese nodules are widely scattered on the floors of all major ocean basins at depths of 5000 meter or more. The nodules range from the size of a pea to bland slabs more than 1 meter across, most are globular and few centimeter in diameter. The greatest concentrations and the best grades of nodules are in the Pacific Ocean outside of the territorial limits claimed by any country. Estimates of tonnage recoverable nodules range from about 50 billion to more than a trillion tons. Where they are abundant, they may be more than 100 per square meter, forming a pavement of only nodule thick. Ferromanganese nodules are internally layered concretions of manganese and iron oxide minerals. They contain several minerals including vernadite, manganite, birnasite, manganite, todorokite, basurite, goethite, agagenite, lepidocrosite and ferroxylite. They occur in various shapes, spherical, discoidal, irregular, etc. Elemental composition wise, they can be manganese rich, iron rich, copper and nickel rich or cobalt rich. Ferromanganese nodules often have a single or multiple nuclei of mud lumps, fragments of older nodules, volcanic detritus or even shark teeth. The ferromanganese nodules are perceived as largest potential resource for copper, nickel, cobalt besides manganese and iron as co-products for the 21st century. Several regions like the Clarion-Clipperton zone in the eastern equatorial North Pacific Ocean with nodule density of approximately 5 kg per square meter and 1.8% of copper and nickel content have been identified as future target areas. Nodules have worldwide distribution in all oceans. Nodule fields have been found in diverse environments such as deep ocean floor, active mid-oceanic ridges, inactive ridges, oceanic seamounts, plateaus, continental borderlands, and marginal topographic highs. Nodules are most abundant in regions of red clay and siliceous ooze, which represent extremely slow sedimentation rate, and virtually absent in regions of turbidites, ice rafted sediments, and volcanic silt, where sedimentation rate exceeds 7 meter per million years. The Pacific Ocean has the slowest average sedimentation rate of all the oceans and is the major area of nodule occurrence. The average growth rate of nodules is very sluggish. Ready availability of potential nuclei fragments, high bottom current velocity that scores sediments and thus effectively lowers the sedimentation rate, activity of benthic organisms intermittently dislodging the nodules from enveloping sediments, and prevalence of higher redox potential at sediment water interface are the deciding factor controlling nodule distribution locally. One enigmatic feature of nodule distribution is their abundance on the sediment surface and virtual absence below 4 meter depth. It is interesting to know the morphology and anatomy of the manganese nodules. Simple spherical nodules are typical of areas of strong bottom current, while asymmetric nodules with smooth upper surface and irregular dendritic bottoms are characteristic of more quiet depositional sites. Internally, the nodules are made up of delicate concentric layering of highly reflective manganese oxyhydroxide and dull silicate rich and iron oxyhydroxide minerals. Shrinkage cracks across mineral layers attest to aging and diagenetic modification. Both athigenic and diagenetic origin have been proposed for the formation of banding. Growth rate of nodules turn out to be around a few millimeter per million year, one of the slowest of all natural processes. The bulk composition of nodules varies from place to place. On global scale, Atlantic nodules are enriched in iron, while Pacific nodules are relatively richer in manganese, copper, and nickel. Within a single ocean, the variability strongly relates to geomorphic, depositional, and basement settings. For instance, within the Pacific, cobalt plus lead enrichment occurs in seamount nodules, higher copper concentration obtains in nodules in subequatorial region, and higher manganese content in nodules on hemipelagic sediments. In central and west Australian basins of the Indian Ocean, both sediments and nodules are found to derive their metals from underlying basalts of different chemistry. Some correlation between nodule chemistry and mineralogy is also apparent, such as that of cobalt and copper with vernadite and copper, and nickel with todorokite and birnasite. Primary sources of transition metals for the nodule are multiple, as dissolved materials from continental weathering and or leaching of the basement and or hydrothermal influx, and as particulate matter like clay adsorbed components and or fecal pellets excreted by the ocean floor biota that extract metals from seawater. The origin of manganese nodules could be hydrogenous, that is, deposition from basinal bottom water. Alternatively, the nodules could be early diagenetic or deposited from sediment pore water, recycling the metals under oxidizing and suboxing condition of diagenesis. Metallurgical studies of the nodules have been designed primarily to recover copper, nickel, and cobalt, though some efforts are also being made to save the manganese. A great deal of time and money have been spent in efforts to develop an economic method for recovering the nodules from the great depths involved. Several groups of companies claim the recovery process to be ready and able to start work at once on a commercial basis. They are being delayed primarily because of political problems. Who owns the floors of the deep ocean basins? No law of the sea yet applies to these deposits. Various groups sponsored by the United Nations have met in Geneva, but they are still reported to be far from agreement. Now, to recapitulate what we learned today, leading producers of manganese ores are Ukraine, Georgia, South Africa, Gabon, Australia, Brazil and India. Geologically oldest sedimentary manganese deposits are encountered only in Brazil and India, and these deposits are of late Archaean age. Early part of Archaean is devoid of sedimentary manganese deposits. It is because of the fact that the early part of Archaean, with an extremely oxygen deficient atmosphere and hydrosphere system, was geochemically hostile to manganese precipitation, though plausibly iron and manganese was substantially released by endogenous high temperature hydrothermal solutions and stored in contemporary deep oceans in dissolved state. Late Archean sedimentary manganese deposits in Chitradurga group of Dharwar Craton, southern India, provided geological evidence for identifying the exact timing of the onset of photosynthetic oxygen in the atmosphere and hydrosphere. The sedimentary manganese deposits of the Chitradurga group are underlined by stromatolitic limestone. The presence of cyanobacteria in stromatolitic oxygen, which evidently induced precipitation of manganese as manganese oxyhydroxide, is not less than 2.5 billion year old. After modest initiation of manganese ore sedimentation during late Archean, the Paleoproterozoic was replete with large size sedimentary manganese deposits. For example, world's largest Kalahari manganese field in South Africa. The Mesoproterozoic was practically barren, while during the following Neoproterozoic time, most manganese deposits are restricted to glaciogenic sequences. Manganese concentrations were relatively small in the Paleozoic and substantially large in the Mesozoic era. During the early part of the Cenozoic era, giant-size oolitic pisolytic sedimentary manganese deposits were formed in Ukraine and Georgia. In sedimentary manganese deposits, manganese occurs as manganese oxides as seen in the limit resident Morocco, Santa Cruz Formation, Brazil deposits, manganese carbonates and manganese silicates. Manganese silicates are not exploited. Supergene oxidation of manganese carbonates in several deposits yielded high grade manganese oxide, for example, Itabira group in Brazil. In several sedimentary manganese deposits, manganese ore beds are interbedded with or overlined or underlined by organic carbon rich black shales. For example, Franceville group, Gabon, Molango in Mexico, Urquit in Hungary. In these deposits, manganese occurs invariably as manganese carbonates such as rhodochrosite, kunthanohorite. These manganese ores were formed under reducing conditions. Manganese carbonate minerals were of diagenetic origin and were formed by diagenetic reaction of dissolved manganese of anoxic deep sea water, originally derived by carbonate in sediment pore water, which was adequate enough to exceed the solubility of manganese carbonates. Black shale free sedimentary manganese oxide deposits are generated through the process of transgression and upwelling of dissolved manganese rich anoxic deep sea water into shelf region or basin margin, where the oxic sea water facilitates oxidation and precipitation of manganese as manganese oxyhydroxides. If similar deposits formed under oxidizing conditions contain manganese carbonate ores, then the formation of manganese carbonates such as rhodochrosite and kunthanohorite is attributed to organic carbon mediated early diagenesis of initially formed manganese oxide precursors. Major land-based Phanerozoic sedimentary manganese deposits are genetically related to stratified ocean system, marine transgression and climate warming. Deep sea resources of manganese with iron, cobalt, nickel, copper occurs as manganese nodules and is 16 times more than that of terrestrial manganese resources. Jai Hind.